Okay, good morning everyone. I'm Vishal Mishra. Some of you know me being in my other class. I'm the guest lecturer for today. Professor Rubenstein is away. So he asked me to cover internet addressing and forwarding. So what has he already covered in class? Has he covered notions like IP addresses, MAC addresses? No? A little bit. Okay. So you have done routing algorithms in this class, right? Things like Bellman-Ford and Dijkstra's algorithm. So you know the concept behind a routing table. So when you did routing tables and routing algorithms in class, what did the routing table look like? What are the entries in a routing table? Maybe you had I'm not sure how. You probably looked at networks something like this. You had nodes N1, N2, N3, N4. Each node had different interfaces. So interface, let's say 1. So if you are at node N1, your routing table would consist of entries like if you want to go to node N3, you have to take interface 1. If you go to node N2, you take interface 2. N5 would be interface 1 and so on. Does this look somewhat familiar of what the routing algorithm said and you came up with the routing table? Routing table basically decides if you are trying to go to a particular node, which of the interfaces you should take to get there according to some metric like the shortest path or minimum delay, things like that, right? So now what we'll do is today we'll try and make it more concrete and see how things work on the internet. And on the internet, what do these nodes really mean? And because of the nature of these nodes, this lookup on the routing table becomes a little bit tricky. So on the internet, what you have are IP addresses. So yeah. So nodes that are on the internet have an internet address which is called an IP address or internet protocol address. And are you familiar with IP addresses, what they look like? So for instance, any machine on Columbia, let's say LAN, would have an IP address of the form 120.59. Something of this sort. So this is a dotted quad notation where you have 4 numbers written in a dotted format, and each of these numbers are 8 bits long. So any address, any machine on the internet has an address of this form where you have a sequence of 4 bytes written out in this format. Now consider a router, let's say on the internet, and this router is trying to forward packets, let's say this machine which has an address of this sort. That router is sitting somewhere in California. Now would the routing table of that router contain the full address 128.59.16.23? Yes or no? No. Why not? Look at this address. This is 4 bytes or 32 bits. If you have a router which has to construct table for every possible node on the internet, then you have to have a table which has an entry for all possible addresses, which is 2 raised to 32, which is 4 gig. No router can possibly store that big a table, and additionally it's an incredible waste of space because those 4 gig entries are not all filled. So some amount of aggregation is done at the router level. Now what's the logical way to aggregate these addresses? So again, let's say this is a router, and all of these machines are in Colombia. Here is this router sitting somewhere in California. All of these machines, these possible machines, are attached to this router N4, which is the gateway router of Colombia. Now it's logical to assume that the shortest path to all of these machines from some other point will follow the same link, right? If there's this router sitting in California and you have this machine here, a machine in the EE department, a machine in IEOR or business school, packets that are starting from California are likely to take the same path, right? So you tend to aggregate addresses in routing tables according to their network, the network they reside in. That level of aggregation is good. That way you can reduce on the number of entries that you need to store. You don't need to store 2 raised to 32 entries in the routing table, but you only need to store entries corresponding to the different kinds of networks that exist on the internet. So there might be an entry for Columbia, there might be an entry for Stanford, there might be an entry for Morgan Stanley. Different organizations which have different networks or sub-networks will have entries in routing tables. So that's the first level aggregation that's done in routing tables. So how many possible networks are there? So in the old days, when the internet was sort of evolving, the old system had classified all possible addresses into 5 categories. You had class A, class B, 5 classes of addresses, and what you did was you looked at the prefix of the address. So if the address started with a 0, it was a class A address. Any address where the 32-bit sequence starts with a 0 would be a class A address. 10 be class B, 110 class C, and 1110 is class D. Class C is reserved. So any address which had 1 to 127.x.y.z was a class A address. Any address which is 128 to 191.x.y.z is a class B address. Class C address would be 192 to 239. And class D would be 2. So when these networks were being assigned, every organization which got onto the internet was assigned either a class A address, a class B address, or a class C address. In a class A address, the network itself had 8 bits free. The 8 bits of the network were free and 24 bits within the network were free. So what that means was that there were 2 raised to 8 possible class A networks. So you assigned a particular class A address to one of these networks, and then these networks had the freedom to choose the rest of the 24 bits for their node in the network. So a class A network would have a unique prefix of the first 8 bits, and then 24 bits following that in the 32-bit address were left free for the network to assign. So that meant that every class A network could possibly have 2 raised to 24 different hosts connected to it. Class B, you had 16 free bits, and class C, you had 8 free bits. Class D was reserved for multicast, so we won't get into that. So what that meant was an organization could only apply for a block of addresses which were either 8 bits, 2 raised to 8, which could give them 2 raised to 8 useful addresses, 2 raised to 16 useful addresses, or 2 raised to 24 useful addresses. Now this classification, people soon realized, was not ideal. This gives you 255 or 256 addresses. An organization, if they applied for a class C address, they had too few addresses for their whole organization. you could at most connect 250 machines to the internet. If an organization got class B address, then they got 2 raised to 16 addresses, so they could connect 2 raised to 16 machines to the internet directly. Now the gap between class B and class C and class C and class A was too much. If you assign a class A address, you have 2 raised to 24 free addresses to assign to machines on the network, and that's roughly 16 million. So no organization is likely to have those many addresses. And so what started happening quickly was that people thought that class B or class C was too small for them. They'd apply for class A and then not use class A at all. So the address space would be very sparsely filled up. Similarly for class B and class C. Organizations, mid-level organizations who thought that class C was too small, applied for class B. They maybe had 1,000 machines connected to the internet, and they were wasting space on the internet. So what happened was these addresses got allocated to different organizations, but they were not using them efficiently. So internet was running out of addresses very quickly. So to address this, there was a system proposed called CEDAR, Classless Internet So in the older days, if you had to do forwarding at a router, if you had to identify a network, you just looked at the first few bits, identified whether the packet was going to a class A, class B or a class C address, and then looked up the corresponding interface in the routing table. So you looked up the first few bits, identified whether it was class A, class B, class C, and then you had individual bills for those networks, and you could forward the packet along. But because this addressing scheme was very efficient, CEDAR was proposed in the early 90s, and CEDAR defined networks with the address in a prefix format. So any network in the CEDAR classification has an address of the form X/Y, where X is the prefix and Y is the network length in bits. So now going back to the Columbia addresses, all addresses on Columbia are 128.59.A.B. You can also write this as and in the CEDAR format it becomes 128.59/16. So 128.59 is the unique prefix for all machines connected to the Columbia network, and 16 is the network length in bits. What that means is that this network has up to 2 raised to 16 possible machines connected to it, or 2 raised to 16 network addresses assigned to this network. So this is the Columbia address in the CEDAR format. UMass Amherst, for instance, is 128.119/16. Now in the old system, your Y was only allowed to be 8, 16 or 24. In the old system, if your Y was class A, then Y would be 8. If your network was class B, your Y would be 16. If your network was class C, your Y would be 24. What CEDAR did was it removed this restriction. So now Y can be anything. Yeah.
Why is not the length of the prefix in bits?
Is the network length in bits.
Same.
So Y is the length of the prefix in bits, but the smaller the Y, the larger is the network, because the number of bits that are available for the network you use in addresses becomes 32 minus Y. So if you have an address of the form x/y, then that means that network has 2 raised to 32 minus y possible addresses in that network. So Y is network length, or the prefix length in bits. So smaller the Y, larger is the network. So what CEDAR did was, CEDAR removed the restriction that Y could only be 8, 16 or 24. Now Y can be anything, 8, 9, 10, 11 and so on. And X is the prefix written out in decimal format, but it's the prefix that should match this network. So examples of such prefixes. (65/8) is a network. That means the prefix length is 8, so it's a class A kind of address, and the bits, the initial few bits, should uniquely match 65 written out in decimal format. (128.19/16) is a prefix. (128.9.16/20) is another CEDAR prefix style address. So what does this represent? It represents a network which has 20 bits fixed. So that means there are 12 bits available. So this network can have a possible of 2 raised to 12 different machines connected to the network in this format. And the prefix bits should match 128.9.16 written out in decimal format. So another way to think about the CEDAR addressing scheme is, now you think of the whole internet address space as one line. So you start from 0, you go to 2 raised to 32 minus 1. Those are all the possible addresses a machine connected to the internet can have. So any point here represents a particular address that a machine can have, starting from 0 and going to 2 raised to 32 minus 1. So you just, and the x-axis is in binary. So now any network in the CEDAR framework can be thought of as a line segment. So line segment is a network of this format, where every address that falls within that line segment is part of this network. So this line segment could, for instance, represent 65/8. The longer the line segment, the more the addresses in this network. So now going back to the routing table. A routing table on an internet router will now look like something. The networks are represented by x1/y1, x2/y2, and so on, and the corresponding interface. And now a representation of the network is in the form of these prefix addresses. So now consider a router which has a routing table like this, and a packet arrives with a destination address. How is the router going to choose the right interface to send that packet out on? it's going to look up this table. It will see a destination address and see and perform a match on this table. Now, on the internet right now, there are roughly 170,000 prefixes. So typical table in the core of the internet might have 170,000 entries. Now, if you're a router and you're processing these packets at speeds of gigabits per second, and you have to look through this table, then you have to do this thing very fast. You don't have too much time to perform the lookup, decide the interface, and then forward the packet along. So this table of 170,000 prefixes has to be implemented in an efficient manner so that you can perform this lookup very quickly. So what are the ways you can perform this lookup? Yeah. Sorry?
Function. Hash function.
Are you others familiar with hash functions? So a hash function is it's sort of like a random function. Given an input, it will give a random output. So it's pseudo random because it's a well-defined function. But given a particular input, the output looks like a random number compared to the input. So the idea behind a hash function is your address comes, which is 32 bits long. So your total number of entries is, you have 2 raised to 32 possibilities of addresses, but you have only 170,000 prefixes. So you have this large space, but in this large space, you're only looking to identify a small subset. So the hash function idea is to take this large space and map entries of this large space to entries in the smaller space. So with a hash function, you could have a function where all the addresses of Colombia match to one particular address here, and then you can just simply look that up. A very simple hash function would be to simply look at the first 16 bits. Yeah.
Won't that not work?
Yeah, so I'm coming to that. A hash function works if all your prefixes are the same. Since these prefixes are varying, a hash function will not work well. So I gave an example of a very simple hash function. So suppose a packet arrives with destination address (128.59.16.23). Now the domain of this address space is 2 raised to 32. We know that this address belongs to machines in Colombia. Now from our knowledge of the addressing, we could simply say that just look at the first 16 bits. If they match 128.59, then send it to the interface which is going towards Colombia. Now that hash function assumes that every address, if you cut off at 16 bits, would give you a unique network. But what about addresses which are of the form x/24? Or x/22, x/17. If you cut off, if you just looked at the first 16 bits, you cannot uniquely identify where these networks lie, or which interface to put the output, to put the packet. So the problem becomes difficult because you can have any prefix length here. There is another problem. So I said you can view you can do any network on the internet as a line segment on this in this space. So any line segment uniquely identifies a prefix address. So another way to hold this information would be just keep a data structure which keeps information of all the line segments that have been allocated. Look at the address and see which line segment the address falls under, and then you'll have an entry corresponding to that line segment. The problem with that is that the way addresses are assigned, you have overlapping line segments. So 128.9, so an example would be 128.9.16. You have three different addresses. One is 128.9/16, this network. You have one prefix which is 128.9.16/20. You have another address which is 128.9.19/24. These three line segments overlap, and they are all valid addresses on the internet. So when you are doing this match, which one should you choose? You have to choose the prefix which is the longest matching. So the one with the highest value of y. Now, how can such a situation arise where you have overlapping line segments like this? Suppose you have an organization like IBM. So IBM has offices in Westchester County. It has research labs in Haifa, in Israel. Research labs in Zurich, New Delhi. Lots of different locations spread across the globe. Now let's say IBM applied for a /16 address and it was assigned 128.9/16. So this is the block that is assigned to IBM, and now IBM is free to allocate addresses within its domain from this block. Now IBM decides to allocate this line segment to all the machines in Asia. And within that line segment, it decides to assign this line segment to all the machines that are in the Tokyo lab. So as far as the internet is concerned, 128.9/16 is all IBM addresses. 128.9.16/20 are all addresses in Asia, and 128.9.19/24 are all IBM addresses in Tokyo. Now if you are a router sitting in let's say if you are a router at Columbia and you get an address which is an IBM Tokyo address, so here is this router. It has different interfaces. The destination address now is the IBM Tokyo address. So how is this router going to decide where to send it? If it decided simply based on this line segment, it might put that packet on the link which is going to Westchester County, which has the maximum concentration of IBM addresses and which is the shortest prefix match. So this is going to Westchester County, this is going to, let's say, India, and this link is going towards Japan. If the router decided to forward based on this line segment, it would have forwarded that packet on the link going to Westchester County. If the router decided based on this line segment, it would have forwarded that packet going to India. The right decision for the router is to look at the longest prefix match, 128.9.19/24, and send the packet along on the path which goes direct to Japan. So the way addresses have been assigned on the internet, you can have these overlapping line segments, and forwarding is done based on the longest prefix match or the topmost line segment that's present in this data structure. So you have to match the longest prefix in the router to do the forwarding. Yeah.
Is it possible that higher line segments overlap two lower line segments?
Yeah.
Two, like the base 65.8 and 128.9, is it ever possible that a line segment that's higher can overlap both of those?
No. Line segments are shorter. I mean, the way, see, the choice to put it higher up was arbitrary. So line segments on top are by definition shorter line segments. So is this part clear? Why would we need longest prefix match? Or you want me to go over it again? So this was just an example that I constructed. On the actual internet addresses have been assigned in such a way that there are overlapping line segments. And to do the right forwarding, you have to go to the shortest or the, yeah.
Why did they overlap? Isn't 1.19 1.16?
I'm sorry?
Top two line segments over there. 128.9.19, 128.9.16.
Right.
So why is that considered an overlap?
So if we write out 19 in binary format, it would be 16 plus 2 plus 1. So that 16 is part of 19. So it is an overlap. If you just look at the bit representation of 19, you'll see that there is an overlap. So let's make that a little bit more clear. So suppose you have a router, and this router is an Internet 2 router. It has one link going to Columbia and one link going towards UMass Amherst. The Columbia address is of the form 128.59. UMass address is 128.119. So if you write 128.119, it will be 1 this is 128. So these would be the first 16 bits of any address going towards UMass 128.119. Columbia, on the other hand, would be So now a packet arrives at this router, and that it's going either towards Columbia or towards UMass Amherst. How does the router decide where it's going? It's going to look at the destination address, and it has to do the longest prefix match. So all these bits, the first 8 bits are going to be identical, whether you're going to UMass or whether you're going to Columbia. 9th bit is also the same. 10th bit is different. So by looking at the 10th bit, you can decide what the destination or which the right link to forward this packet should be. Have you looked at the prefix match algorithms? Have you encountered binary search trees? So one way to implement this prefix match is by implementing a binary search tree. So in a binary search tree, you have a balanced tree. You start at the root node, you look at the address, and then you travel left or right depending on what current bit is. So 0, you travel left, 1, you travel right. And whenever you have a prefix match, that node would be a leaf node, and that would give you a destination address. So for instance, if you were looking for a prefix 0110, then on this tree you will travel 0, you'll go left, you'll go right here, then you'll go right and then left. And the entry here at this node should give you the interface associated with this prefix. So for any search that you want to do, any prefix match that you want to do, you have a binary search tree. You travel down this tree according to the bit sequence that you have. And when you encounter a leaf node with an interface, that tells you that this prefix is matched and the interface that you need to use is given by this node. This is a basic binary tree. Now, if you look at, yeah. Yeah, this binary tree is a data structure. So you can't really implement table lookup. You have to implement table lookup efficiently, right? So if you have 170,000 entries, what's an efficient way to do it? So by having a binary tree, you can in at most 32 steps do the match. Yeah.
If you use multi-level hash, like hash to crop various, and then if you have more, you can hash some more if necessary to try to get, if you're trying to make that.
Say that again.
Hash, and you get one of the low line segments.
What are you hashing on now? The whole address?
No, you hash on a part of the prefix. You hash on more prefix until you get something. You go as far as you can, as long as matching the place you can find something to hash to that's existing. Did you make that work?
So you can actually do that in parallel. You can hash on the first 8 bits, you can hash on the first 9 bits, and things. I mean, you can have multiple hash functions, and whichever one gives a match, the top one that you select as the right answer. So you can do it using multiple hash functions too. But here we're trying to do it using these search trees. Now, if you implemented a binary search tree and you have this router, how many comparisons do you need to do? To come up with the right answer? Yeah? 11. Okay. Is there a way to do it more efficiently?
Forget about the second bit.
So you can forget about the first few bits and just look at this bit directly. That's what you're suggesting, right? So how do you do that in a binary search tree?
Be the 128, which starts there.
So you can start the root to be, let's say, the 9th bit and start from there. So that is the basic idea. So binary search trees can do this job, but there are more efficient data structures based on the tree, which not only let you compress the data structure, but also let you do faster comparisons. And those data structures are called, they are also called trees. And this tree comes from retrieval. So you can think of a tree as a compressed binary search tree, where some nodes and edges are missing. So if you were implementing a data structure which just decided between Columbia and UMass, then You can start from the 9th bit, or if you start from the 0th bit. You could just compress this part where they are all zeros into one node right here. You can compress a series of nodes and edges into one node, and then at that 10th or 9th bit you could make the decision whether to go left or to go right. So that's one way to implement a faster way to implement binary search trees, by using these things called trees. Let's look at a concrete example. So before we look at the example, so now all addresses in your routing table, which are x/y going to a particular interface, all of them are translatable now into this format, where you have some bit sequence 0, 1, 1, 0, and star after that going to some interface, 0, 1, star going to another interface, and so on. So your routing table now is just a bunch of prefixes matched with a particular interface, and your data structure has to match the longest bit sequence to the destination address. So now your routing table looks just like a sequence of interfaces, and you have to match your destination address to the longest sequence in this data structure. So let's say you had a routing table where you had 4 interfaces and 4 prefixes. So 1, 1, 1, star, now what the data structure look like for this example? Well, the root node has no left child because none of the prefixes have a 0 as the first bit, so it only has a right child. Now this node will have both a left and a right child because the second bit is 1 in one prefix and it's 0 in a number of other prefixes. Let me redraw it. This is what a data structure to implement this table would look like. Now suppose you get a destination address and 5 bits are 10111. How are you going to decide the right interface from this data structure? Yeah.
You have to go back to phase 2 after the.
I'm sorry?
It looks like you would have to go back to phase 2 after going because the fourth phase is not here.
So okay. So what you do is you start at the root. 1 will take you here. 0 now takes you here. Third bit is 1. That takes you here. Fourth bit again is 1. But this node has no right child. So you couldn't have matched the prefix 1011 star. The fourth bit had to be 0 for there to be a more specific match than 10. So the algorithm to use in matching a tree is simple. Walk down keep track of last interface seen. Stop when So as soon as the node has no child, you stop and you recall the last interface that you had seen on the walk. and that will give you the longest matching prefix. So you can try for any prefix here. Let's say this was your destination address. So you'll start here, 1, 0. You keep track that you saw interface 2 here. Next bit is 1, you go down here. Next bit is 0, you come here, and now the last interface seen becomes interface 3. Now since this node has no left child, you stop here, and the last interface seen was interface 3. So interface 3 is the right interface for this destination address. Should we repeat the process of constructing a tree and doing a match? If you want me to explain any specific part. Yeah.
How does the router know what prefixes
Are available on which are not. I mean, how does the router know when the prefix is found? How does it get that table?
So that table is constructed from your routing algorithm. So from the address allocation, you know that these are the addresses that have been allocated on the network. Yeah.
What happens if you change the node that goes to interface 2 to 100, and then change your destination address to 10?
So you do 100 star.
And then change the destination address to 10111.
Okay, so 100. So now and now you want me to 10?
10111.
Well, this is not a valid prefix here because it doesn't match anything here. Possibly your routing table has something like a default and some default interface. So the root node might have a default interface, and you'll forward that if nothing matches to the default interface. So this tray, the basic tray is called a radix tree. There's something called a Petrus tree. which saves on space and also the number of comparisons here. So for the same routing table, I'll draw the Patricia tree. And in the Patricia tree, each node also identifies the bit position that it's looking at. So what Patricia tree does is it collapses nodes on the basic radix tree. So now you have only 3 comparisons to do, or 3 bits to check: bit 2, 3 and 5. So you check bit 2. If it's 0, you go down here. If it's 1, you come down here. After bit 2, you check bit 3. And after checking bit 3, you don't need to check bit 4. The only difference that exists in this table after bit 3 is at position 5. So instead of checking position 4, you check position 5 and then you identify the particular interface. So Patricia tree is a more efficient way of implementing radix trees, and it can also yield faster search times. The algorithm to look up on a Patricia tree is slightly different though. So if you're going to look up 1 0 1 1 1, you start at bit 2, you get 0, you come down here, and there's interface associated with that. Now, because it also has a child, according to the old algorithm, you have to go down because bit 5 does have 1 and there is a child, there's a right child at bit 5. So you go down 1, you check if it's 0 or 1, if it's 1. But this position, interface 4, is for 1 0 101. This bit which we skipped causes a problem here. So you cannot use the older algorithm. You'll at the end you'll have to do an exact match. If the exact match doesn't work, then you have to backtrack. So Patricia tree allows you data compression, compression of the data structure. It gives you faster searches, but sometimes you have to backtrack. So the implementation is a little bit more complex with the Patricia tree. In general, if you are asked to construct a tree given a prefix table, then what you construct is this kind of a radix tree. Any more questions on this? Okay, we'll stop here.